So this is the strength of participants, so they're more likely to join. Okay, let's wait few more minutes for others to join, then we'll start. Okay, so I think this will start now. So good evening, everyone, and welcome to the session. This session is about week 7 of MLT. So first, let me share my screen. Yeah. Okay. So week 7 is all about actually 3 major parts is covered in week 7. 3 major parts is covered in week 7. First is softmax regression. Second is generalized linear models, and third is KNN. Okay, so firstly, we will briefly revise all these things, and then we'll go to the assignments. Okay, so this is the agenda of today's meeting. So let's start with softmax regression, and then we will go to ZLM. So how many of you have already watched the lectures and watched the content of week 7? Have you seen or not?
So I've just seen the first lecture.
First lectures, okay. So you haven't seen your lectures, right? So let's revise what is there in week 7. So you can see your lectures and start solving the assignments. So first we will cover softmax regression, then we'll go for KNN and ZLM. Before coming to the softmax regression, let's revise so that we can connect what's happening inside the softmax regressions. Okay, so softmax is actually the extended part of logistic regression. In logistic regression, remember we only use the binary classification, right? It's only for binary classification. So we will extend this notion for the multi-class classification problem. Okay, so how we can do that? So it will be covered in softmax regression, and GLM is generalized linear models. We will have more generalized version of linear models. Give me 1 minute. Yeah, okay. And KNN is algorithm, that is instance-based algorithm. We will see in the last section of this meeting. So let's start with revising the content. So remember in So in the linear regression, what we have done in linear regression, we assume that the data is continuous, right? Because it's a regression problem, so data is labels. I mean, it's supposed to be continuous, and we make assumption that all the features are independent. And even though they are not independent, we try to make sure that the independence between those, right? The correlation between those is the very minimum. if there are features that are correlated to each other, we try to drop those features, right? And the second assumption that we make, that by the labels are continuous variables and the distributions of continuous random variables, we suppose they are coming from the normal distribution. This is the main assumption that we make about the linear regression problem, right? The data is continuous and the distribution that they follow, I mean the by given x, given the input, the data labels supposed to be follow normal distribution with some mean and sigma square, right? So this is the main assumptions of the linear regression. And we try to find out the relationship between the labels and the inputs. And we suppose that there is a linear relationship happens between the labels by and in the features. So we assume that there's linear relationship between the features and by, and we try to optimize this this linear relationship, this model. We try to fit this model, right? So this assumptions we make about the linear regression model. Even though if they are not linearly independent, we try to transform a feature into some other feature space, some other transform space, and we try to find the linear relationship between that transform space and the labels. So actually we are trying to fit a linear model between the features, I mean the linear relationship between the features and the labels. So this is the main idea behind the logistic regressions. But when we talk about the classification problem, in the case of regression, the labels are continuous. That so all these things looks very intuitive, right? We can have such relationship, linear relationship. This makes some sense. But what about the classification problem? In the case of classification problem, by supposed to be categories or different classes, right? Let's say for binary classification or multi-class classification problem. So in those classes, the distributions of labels is not normal, right? And we cannot have such a relationship between features and the label, because they are not numbers now. They are different classes, different categories. So what we do in the classification problem, we try to find a separating hyperplane that separates those different classes, right? And we assume those separating hyperplane. The separating hyperplane is a linear functions of features. So that W transpose X is this hyperplane is supposed to be linear in the features, right? So again, the linearity come into the picture. Here we are trying to find the difference. Yeah, Abhishek, you are trying to say something?
Yes, sir. Sir, just one question here. In the linear regression model, we assume that y given x will take normal distribution with whatever mean it is. So in every linear regression, we do that.
Yeah, this is the first assumptions of the linear regression model. Okay, we will generalize this as well. This assumption we will generalize in the generalized linear models, but for the sake of the linear regression model, we suppose that the labels are coming from the normal distribution. That's why these models are called parameterized. Why? What does it mean? These models are parameterized. We assume some distributions of the data set. Okay.
Okay.
And in the behavior, most of the time you see that normal or Gaussian distribution come into the picture. That's why this assumption is very intuitive to make and very good to make, right? But we can generalize this model as well. We can generalize this assumption that we'll see in the next part.
Okay, sir. Because I asked this question because previously we have done this linear regression a lot, but we
We
didn't go
certainly
into the
don't, yeah. So we generally don't give much importance to that assumption, right? But this is the assumption that we make for the linear regression model.
Okay, sir. Thank you. Thank you very much.
Okay. So we were talking about the linearity between those. So here we can assume the linear relationship between features and label, but in the case of classification, because they are classes, they are numbers. In the binary, they are 1, 0. In the multi classes, they are 1, 2 up to k. So they are numbers, not the real numbers. So and remember, this relationship will give you some real numbers. So rather than defining such relationship, we try to find out the separating hyperplane, and we assume that separating hyperplane is the linear in the features. So if you have two features, then the separating hyperplane is actually a line, right? So again, this separating hyperplane is the linear model. So again, the model is linear and we try to optimize this model. We try to fit this model, right? So up to here, we have only linearity into the picture. Okay, what about distribution here? Here we are assumed that by given x comes from the normal distributions, Gaussian distribution. What about these? If they are binary, then by given x comes from the Bernoulli, right? It's very easy. It's very intuitive as well. Bernoulli, because if there are only two classes, 1 and 0, then 1 occurs with some probability p, then 0 occurs with the probability 1 minus p. So the distribution of by given x can be assumed to be Bernoulli. And in the case of multi-class classification problem, the distributions of by given x can be assumed to be multinomial. So what is multinomial? We will see in a while. What is multinomial distribution? So in the case of multi-class classification problem, by given x is assumed to be multinomial. And in the binary classification, the distribution of the by given x is assumed to be Bernoulli. So keep these points in mind. Okay, so all these models are called parameterized because we make some assumption about the distribution of those data set. Okay, now let's move ahead.
Sir, can I ask a question?
Yes, sure.
Sir, why do we want to make an assumption? Like, how does this distribution help? And like, why do we make this assumption?
Okay, so actually what the data set is actually we are predicting something, right? We are predicting that that class, or say that example, belongs to that distributions. Once we have organized, or we have found out that this data set is coming out from this distribution, then we can easily predict for some new examples, right?
Yeah, got that. But shouldn't that is the role of the model itself, right?
The model itself. But so your question, how that helps in defining models, right?
Yeah.
Okay, so for this, just wait for the second part of this this meeting or this session. We will see in the generalized linear model how that distribution come into the picture. Okay, we will try to generalize these things. Now we are making some standard assumptions, right? That it comes from normal distributions, it comes from Bernoulli, it comes from multinomial. We will try to generalize all these things. Okay, give me 1 minute. Okay, so sorry for the interruption. So we were talking about the classification problem, right? Now we will extend this to the logistic regression. So can anyone please tell me what happens in the logistic regression? What
So
happens
we
in the
transform
logistic
it with the sigmoid function. So
regression? We transform what?
we transform the feature.
We transform the features. No, we don't transform the features. We transform. Actually, we use the linear combination again. we suppose that W transpose X, we take the linear combinations of the features, and then we apply the sigmoid function to that, right? And we say that these sigmoid functions give you the probabilities for the classes 1 and 0. Okay, so what is this? This is 1 upon 1 minus 1 plus e raised to power minus omega transpose W transpose X. So this is the linear combinations. So actually sigmoid Z is 1 upon 1 plus e raised to power minus Z. This is your sigmoid function. So there are some properties of this function. So one thing is that actually this shape of this is something like S, and the values of this functions belongs to 0 and 1. Belongs to in between 0 and 1. And the shape is something kind S shape. So remember, this is your hyperplane, and we using the some activation function to that hyperplane, we squeeze it into some kind of S shape. It's not perfectly S shape, but some kind of this shape. Okay, so remember that W transpose X was giving some values in between minus infinity to infinity. So these values doesn't make much interpretations about what it's actually giving, right? But once we will we transform these values using some activation function called sigmoid function. Then these values comes under between 0 and 1. And the next part is that the sum for p y equal to 1 given X is actually 1 upon 1 plus e raised to power minus omega transpose X, and the other part will be 1 minus. So the sum of these two probability of these two classes are actually 1. So we can interpret these values, these outputs, sigma W transpose X, this output you can assume as the probabilities. We can interpret it as the probabilities for the classes. Okay, so one way is to interpret the logistic regression in that way. Another, you can think we make some assumption about the logistic regression. Till now, what we have assumed that the level are associated with the linear levels in the remember in the linear regression we assume that there is linear relationship between the features and the output, right? But in the case of classification logistic regression, so it applies for the binary classification problem. Here actually with using this this function, this model, we try to model the probabilities, not the labels, because here are classes. So we try to model the probabilities. Okay, and here the assumptions make is that the odds. What is odds? Odds is actually nothing but the probability of success divided probabilities of failure. Okay, so this is called odds, and the assumption that logistic regression make is that the log odds are linear in the features. So log odds are the linear in features. So this is the assumption that logistic regressions make, rather than the actual classes by the log odds are linear in the features. So this is the assumption is made. So what is log odds? This is probability of 1. And this is the probability of 0. So let's say this is p, so this will become 1 minus p. So here this will become log p 1 minus p W transpose X, right? So this is the assumption that log odds are linear rather than the by being linear. Actually probabilities odds, the log odds are the linear in the features. Okay, so if you solve this this, you will get that p is 1 upon 1 plus e raised to power minus omega transpose X. Just solve this equation, and p is what? This is the probability of y equal to 1 given X upon 1 plus e raised to power minus W transpose X, right? And so y equal to 0, it will become 1 minus of this thing, whatever, right? Now this is for the binary classification where we can define log odds. What about the multi-class classification problem?
One doubt, sir. So if we substitute P in that, then it'll come to that W transpose X.
Sorry, can you
If
please
we substitute P in this log P by 1
no,
minus.
just solve this one. Just solve this one.
We
So
just need to solve it. Okay, right.
This will become P 1 minus P upon e raised to power W transpose X. So here P is equal to e raised to power W transpose X minus, right? So it will become minus P e W transpose X So if you take P here, so it will become P 1 plus E W transpose X upon E W transpose X. So take this in the denominator, 1 plus E. So this will become 1 upon 1 plus E raised to power minus, because this will become 1 and this will become 1 upon this W transpose X, right? So this is your P.
Okay.
Okay, so my point was that rather assuming the linearity between the levels and the features, we assume the log words are the linear between features, have linear relationship to the features. Okay, so this was the point here. Now we can do this in if we have only 2 classes. What about multi-class classification problem? How we can extend this to the multi-class classification problem? And one more thing, in the case of linear logistic regression, now we try to fit this function. We try to fit this function sigma z. Okay, so for this, what optimization procedure we follow? Maximum likelihood estimator, right? Given is sigmoid, what is the likelihood of the data set of the data? Given a sigmoid function, we will find this. So this is the likelihood. We try to maximize this thing. So by using this optimization procedure, we try to find out the optimal weights, right? And that's how we will fit the this sigmoid function. Now, in the multi-class classification problem, how you will apply this thing? So assume we have k classes. So this comes under softmax regression.
So in multi-class, we should take linear combination of each class.
Okay.
And then find the probability of each class. And
how you will find those probabilities? Here we have applied the softmax, sigmoid function. In the case of multi-class classification, we apply the softmax function.
Okay.
Okay. So what softmax function? Let's see. So assume you have k classes, 1, 2. Okay, you have k classes. Okay. So what you do, for every class you find the linear combinations. Okay. So let's call those by k, by I. So by I, this is the linear combinations I'm calling. Not just call by I, just call it Zi. So by I we can say at the last output. Okay. So let's call it Ji. So let's call it Ji. So the notation that sir has used in the lecture is something like that. So it denotes the linear combinations for the ith class. Okay. So this is what? This is Bi. So this is the intercept plus W, and here we have used the notation something like B for ith class, and the jth component of weight vectors and the jth features. So this kind of notation is used in the lecture. So I'm using the same notations, just not to make things messier. Okay. So these are the notation used. So notation says this is the that linear combination for the ith class. So for k classes, we have k such linear combinations. So Z1 will denotes the B1 plus W1 1 X1. So X1 is here the first feature. You have M features, right? So plus W2 1 X2 up to W M1 Xn. Here, so these are intercept. This is your first weight vectors for the first linear combination, right? So here this index denotes the class, and this index denotes the feature. Okay, so first feature corresponding to the first feature, this is your first weight vectors. For second feature, this is your second feature, and similarly for Z2, this is the second linear combinations, because for k class combination you make k combinations, k linear combinations. Okay, so this is B2 plus W. Again W1 to X1. So not to confuse between within these notations. That's why I'm rewriting all the things again. 2.
So these weight vectors are actually the probability, right?
These weight vectors are actually the
probability.
No.
No.
Once we are finding those linear combinations, the probabilities will be once we have passed through these outputs using the softmax functions, then those values will be the probabilities.
Okay.
Okay, so up to here, this is, it will look like W M to X M. So there any problem in this kind of notation? So such you have k linear combinations. Okay, dk up to same thing. Okay, now what we will do, we will pass these values. Remember in the logistic regression we have just done for the one. We will come to that by we are not making two linear combinations and how only one will work. So this is the actually a standard version of logistic, is the standard version for the softmax regression, that we can use only one linear combination rather than two. You can also use two linear combination as well. The result will be the same. Okay, so here such we have found k such linear combinations. Now we will pass those using this in the logistic regression we have passed using.
So I didn't get
functions.
it. Can you just repeat what was the assumption again? Going a little faster.
Which assumption?
You said in the. Could you repeat the last line? I missed it out completely.
No, so what we have done in the, I'm trying to connect between logistic regression or softmax regression. So in the logistic regression, what we have done, we have found the linear combinations of the features and then applied the sigmoid function to that linear combinations, right?
Right.
And we are calling those the probabilities for class 1 and 1 minus those is the probability
That's
for class
clear.
0, right?
Right.
But in the case of k classes, what we will do, we will find rather than finding one linear combination, we will find k linear combinations.
Okay.
Okay, so there we were trying to fit k plus one weights. Here we are trying to fit how many weights? So here we were trying to find n plus 1 weights. So there we are trying to find for each linear combinations, how many weights are there? M plus 1, right? And how many such linear combination we are making? K.
K. Right.
So k into m plus 1 weights we are trying to fit. We will fit.
Okay.
Right. Okay.
Sir, are you considering the B1, B2 also to be weights here?
Yeah. This is the intercept.
Yeah, intercept. The bias term is also a weight.
Yeah,
right?
bias term. Yeah, it's a weight. So some different notation are used in the lecture. That's why I'm using the same notations. Okay. Now, so what was the next part in the logistic regression? We passed the linear combination in the sigmoid function, right? Here we will pass the we will pass those linear combination through the sigmoid function. So what was the sigmoid function? Sigmoid function was e raised to power z upon 1 plus e raised to power z. So here what we will do here in the softmax function, what we will do for e raised to power, let's say z2, zi for notations, what it will do. So here e raised to power omega transpose this one, this linear combination. So this linear combination I'm calling zi. Okay, so let's call it zi e raised to power zi, the linear combinations, okay, upon the sum over all such linear combinations, e over z, let's say j, and j is varying from, so all such linear combinations, so j is varying from 1 to k. Okay, so this is your softmax functions. So remember, in the denominator is same for all such functions, only the numerator is changing. The denominator is the sum of all such linear combinations, and the denominator is corresponding e raised to power such that linear combination. So such if you pass these values here, you will have k values, right?
This I is coming in 1 to k, right?
No, I is I is fixed here. J is varying from 1 to k. This j is varying from 1 to k. This I is fixed here.
What is I in the above equation?
So we will find sigmoid softmax function for z1. We'll find sigmoid function for z2, and up to we will find sigmoid function for zk. Okay, right. So denominator is a sum of all such linear combinations and e raised to power those. Okay, I mean, so e raised to power linear combination and sum over those. Okay, and the numerator is what? E raised to power that linear combination corresponding to that class.
So, but wouldn't the denominator become 1 when we sum over everything? It wouldn't, is it?
No, it wouldn't.
Okay.
Sir, is this similar to the odds function that you had written for logistic?
Similar to what?
The odds function.
Yeah, odds function. But in the case of in the case of two classes, we have success upon failure, right?
So here the first numerator is success and the down is all the failures.
No, it's not failure because the if also is adding here. If component is also adding here.
Okay.
Okay. So these remember in the sigmoid function we call this as the probabilities of y equal to 1, right? And other is always easy because we have only two classes. So y equal to 1 will become probability of y equal to 0. So here these values become the probabilities. So these values become probability of y equal to 1. This values become probability of y equal to 2, and this probability become p y equal to k. So up to here, any problem? So remember these values are between 0 to 1 because this is the sum over all such combinations. I mean e raised to power linear combination of all these and sum over these, and this is the part of this summation. So this gonna be in between 0 and 1 always. And if you sum over all such k classes, so what will be the value of those? If you sum over all zi's, sigma zi's over all such classes, what will be the z?
1.
1, because the numerator will also become the same as denominator, right? If you sum over all such classes, then it will become 1. So remember, it is again denoting the probabilities. So this you can think as the probabilities of class 1. This you can think as the probabilities of class 2. This you can think as the probability of class k. Okay. So now you can connect these using logistic regression. Hello.
Sir, in the last part, sir, I am having problem. Like, can you repeat the last part? So I am saying you like what I have understood. So first we are doing a linear combination for each class. We are doing a linear combination, and we are using each m plus one weight vectors for one class. And
Yes.
if we are doing it over k number of classes, so we are using k into m plus 1 weight vectors.
Yes.
That is understood. Now we are doing the we are applying sigmoid function on the
No, that is called softmax function, not sigmoid function.
Sir, here actually I am confusing. Like up till weight vector it was okay. Then where like this sigma of sigmoid function of zi, this we can write in the form of e to the power zi by summation of all the
E raised to power
zi.
zi's. Yeah.
E raised to the power zi, summation of all that. So from there we will get so from there we will get a probability of that zi or proportion. What we will get from
Probabilities of class, probability of that class.
probability
That sample
of
belongs to that class, right? So if let's say some example x come, some new example x come, or say example from the training data set comes, right? So if you will find sigma of z1, sigma of z2 up to sigma of zk, so this will give the probabilities that this examples belongs to this class 1, right? So let's say some probabilities come at 0.75, 0.05, something like that, 0.05, okay, something like that. So there is 75% chances that this example belongs to this this class 1, okay?
So that we will write like p of x given 1 y equal to 1.
P by equal to 1 given that x. Okay.
Okay, sir.
So now our task is to find those weights, right? Now we have model with us. Now our task is to find the weight vectors. So what we have done in the logistic regression to optimize the weights or to fit the model. What we have done in the logistic regression for the optimization?
Used MLE.
MLE, right? And so can we apply something like that in the multi-class classification?
Yes, sir.
Yeah, so same kind of thing we will apply. And the loss function here, it is called, you can call it log likelihood function, but the most common name for this is called So we will see how this is called log likelihood, and this function is called cross entropy function. Okay,
Cross
so what is this?
entropy, we were told, is just negative of log. Like
Yeah, negative of those functions. So this is what? This is by I. Cross entropy is by I log. So this is by I log the prediction. Okay, and some of our all such classes. Here it is by equal to 1 to k. So these are here. This is the actual class, and this is the predicted class. Okay, and we will find. So loss is always considered to be the function of weights, right? So weights are here w and b. So this will become summation over by yi log prediction by I hat, and over such all k classes. And we will sum all such for all the examples. Okay, so example will also be, so here notations, what notations we have used. So we can call those so here these values we can call as a predictions value, because these are the predictions. So we can call this as this we can call it by one by one head. This you can call it by two head. So you can call it by k head. So this is actually the likelihood, or not likelihood, the probabilities for the class 1. For probability for the class 2, this is the probability for class k. Okay. So here, the same thing we have used. So this is by I. This is our. Let's say this is j. So let me rewrite this. So this will become by I. I belongs to example, and this is for class j. And we will sum over all such classes log by I hat class j, and j will vary from 1 to k. So we will write for all such k classes and sum over all such examples. How many examples? N examples are there. Okay, so this is your log. This is your loss. Okay, so now notice in that this is the actual prediction. So this will take value either 1 or 0, right? So if this example belongs to class, let's say it belongs to class j, then by j will become 1, and all other by 1 up to by k will become 0, right? Except by j. So this reduced to something like that. This reduced to, actually this is minus. Okay, so this is minus. This will reduce to something like that. Some log by j for that example, and the prediction, and some over all such examples. Okay. So what you have to do, finding the loss, what you will do, you just take the maximum of this. So how you make predictions? For one examples, you have find all such k values, by k values, probabilities values. So how you will make prediction? The maximum probability you will predict into that class, right? So once you have found all such k values, so you will find the maximum out of this, and you call those that example belongs to that class. Let's say if that by 2 is the maximum. If the by 2 is the maximum, then you can say that example belongs to class 2. Okay. So how you will write loss function? You just take the maximum probabilities and take the log, negative log of this, and sum over all such examples. Then that's how you will find loss function. And so what actually entropy gives? Actually, entropy tells you the randomness in the data set. So this captures the randomness in the data set. Randomness means that, let's say you have two boxes, and here you have three classes, balls from three classes, red, blue, and green. So you have 50 red balls, 50 green balls, and 50 blue balls. Okay, 50, 50, 50. And in the another box you have let's say 10 red balls, 5 green balls, and let's say 100 blue balls. So which one is more random? this much is random or this much is more random?
Second one is
more random or first one is more random?
first one will be more random because second one, this blue balls.
Here we have more certainty that the ball will be blue, right? Because most number of balls are the blues. So probabilities here is very close to 1 for blue, right? Here you have equal probabilities. So here you have probability 1 by 3, 1 by 3, 1 by 3, right? So there is more randomness, more uncertainty, right?
Yes, sir.
So this equation actually captures the randomness in the data set, right? So so this is how this pi log pi sum over all these things. This expression actually captures the randomness in the data set, right? So if the values become close to 1, this become maximum, right? And we want to reduce the randomness in the data set. We want that this probabilities goes close to 1, right? So actually your loss function is looking like minus summation over log yi over 1 to n. So you want to minimize loss because this is minimum of this thing. So you want to maximize this thing, right? So you are maximizing this thing that on what is this? This is the probability that example belongs to class I, right? And you are maximizing these probabilities, right? So this how that makes sense. Minimizing loss means you are actually maximizing the probability of that example belonging to that class. Does it make sense?
Actually, sir, yeah, if you can slow down a bit, it would be, I think, it would be really helpful for all of us.
Okay.
Okay.
So my statement was that minimizing loss is equivalent to maximize the probability of that example belong to that class.
So
Does this make sense?
Yeah. So basically, what we are saying is the maximum probability which comes out after we pass through the softmax, transform activation.
Yeah.
Is actually minimizing the loss.
Yeah. So actually, we are finding such k probabilities, right, for each and every classes, and we are trying to maximize that example belongs to that class, that ith class, jth class, whatever that is. Okay.
Right.
So this expression makes sense from this particular expression, this particular statement. This makes sense, right? Minimize this. It actually maximizing this by i's.
Yes.
Okay. So this is called gross entropy loss.
Sir, here yi is?
Yi is the probabilities. Actually, this is sum over. This is actually by. This is sum over by k by j log by at k j. And this is error for considering one example. So remember, this gives value 1 and 0. So I'm just reducing to this part because it is 1. This is the actual probabilities, and this is the predicted probabilities. This is the actual class, and this is the predicted probabilities.
Right? Actual probability. So that is.
This is not actual probability. This is actual class. So it is 1 class, and 0 otherwise.
Okay.
Right? If it is belongs to class
it is
J,
like an indicator function, right? Either it is so okay.
Yeah. So actually, if it belongs to class J, then we are trying to maximize that probability that it belongs to class J, right?
Yeah. Okay.
Got it. So this equation, what you have just shown, can we interpret it as prior into the
exactly. So this is your log likelihood,
right?
This is, so again you can call it the log likelihood.
Right.
Okay. So now you can connect this using logistic regression, right? In the logistic regression, we have used maximum likelihood estimation. The same thing we are using, just in the different manner. We are calling that cross entropy because it captures the randomness. Okay. Now the main part here is finding derivatives of this loss function. So as we said, none of you have pause the lecture yet. So it would be nice if you have already seen the lecture, then how to find derivative, because it's all mathematical. Okay, so let me share that screen now. Okay, so can you see my screen pull up file?
Yes.
So now we have model, now we have those functions. The next part is come the optimization. Okay, so optimization, for optimization, we will use SGD or the gradient descent method. Okay. So this is your model, regression model here. So it's the generalized logistic regression model for K classes. Okay, so some different notation here is used. So what we will do, for if we have M features, we will take M C classes here. C classes are taken. So we will find C linear combinations, and these C linear combinations are passed through the softness activation function, and we will get
basically that sigma is basically W transpose WX, right?
W transpose X, yeah.
Yeah.
So these are the linear combinations. So these linear combinations are passed through the softmax activation function, and we will get the C values. So we have used K here. So here it is C. We use C values here. So what these C values denotes? This denotes the probabilities of classes, different classes, right? So this is your model.
Then again, that softmax function is that e raised to power z upon sigma
e
of e raised
to power that input. You can think now this as the input. So e raised to power that input upon the sum over all such
inputs. Yeah, got it.
Right. So here training data is okay, model is okay, loss function is okay. For the illustration, we have used this data set here. Yes.
Can you go on the up on the diagram?
Okay.
Yeah, I have one quick question. So whenever we take the probability to convert that bunch of the data, actually we converting through the probability ratio, no, at the end in the softmax activation. So the question is that why they choose that particular exponential series as the function? Why not normal either logarithmic or the normal probability? Like that I divided by summation of I instead of e to the power I divided by summation of e to the power I.
Okay, so this is the basic assumptions that logistic regression follows. Rather than we initially make assumption that the stepping hyperplane is the linear combinations of features. Okay, in the case of linear regression, we make the labels are linearly related to the features. But in the case of logistic regression, because they are classes, we cannot make such linear relationship between the classes and the features. So what we will do, rather than finding the relationship between classes, we are finding the relationship between the probabilities and the classes. Sorry, probabilities and the features. Okay, so here rather than probabilities, we are making assumption that the odds are actually the probability of success upon probability of failure. So these odds are linearly related to the features. Okay, so these assumptions are made in the case of logistic regression. From there, that sigmoid function come into the picture.
Sir, is there any intuition behind odds? Like, why are we using the probability of success upon probability of failure?
So, actual reason, actual interpretation behind that, I'm not sure though. But that's pretty sure that we are finding the linear relationship between the log odds and the features.
Actually, in real life, it is used in betting, sir.
Yeah, odds are used in the
odds are used in bettings, horse racing, and also they use in betting. So they use odds.
Odds makes more sense than probabilities in the case of such betting kind of problems, right? Because higher odds gives that the probability of success are more and more than the failure. Actual probabilities may sometimes make confusions because probabilities are between 0 and 1, right? So some probabilities 0.7, 0.3. So we can surely say that this probability of success is higher. But how much higher than the failure? That ratio can be captured using the odds. Okay, so let's say you have very higher odds. Odds can be up to infinity. Okay, 0 to infinity. So if you have higher odds, so in that case, you can say that the probability of success is way higher than the probability of failure. Okay. So such kind of interpretation we use odds rather than the probabilities.
Sir, also in the first lecture, professor talks about least square classification and logistic regression and the softmax regression, all these classification problems following exponential distribution. Is that the reason why we use that e raised to things? Sir?
Yeah,
Could that be the reason?
Yeah. So you are talking about the lectures of week 7, right?
Yeah, week 7, the first one, sir. That's the only one that I watched.
Yeah. So yeah, we will come to that part in the next generalized linear model. So first I'm trying to see the softmax activation from softmax regression because it's the extended version of the logistic regression. Then we will come to the generalized linear models. Okay.
Yeah.
Okay. There also that part will come. How that odds is coming into picture. Linear relationship between log odds and the feature. That part will also come there in generalized model. Okay.
Sir, here in the targets, we are getting the probabilities of each classes, right? So, and from there we are taking the maximum. So, like, what is this maximum, sir, maximization?
So you have different probabilities. So you say that T1 is the probability that this example belongs to class 1. T2 is the probability that it belongs to class 2. TC is the probability that it belongs to class C. So how you will make predictions? Which has the higher probability, right? The one which has the higher probability you will classify into that class. Let's say T2 is the highest value. So it means that there's the highest probability that this example belongs to class 2. So you will predict that example belongs to class 2. Higher probability, right? Just higher probability means that it belongs to that class.
Yes, sir. Yes, sir.
And one more question, sir. In here, the last thing is written argmax. So suppose the softmax is that function which is converting everything in the probability. Is that certainly possible? T1 to TC, there is a more than one features.
You mean the ties happens?
Correct. And argmax is the mathematical calculation which is giving the argument of that which one is the max. So which is returning only one thing.
So that is random choice. Actually, if that any ties happen, like say T1 and T2 are the same and these are the highest values, then the randomly we assign one of these classes.
So
there's
that's
no hard and fast rule that if their ties happen, then it should go into that class. There's no such any hard and fast rule for that. Just randomly assign one of those classes, or let's say the very first class we assign to that class. It's again a random, right?
Yes.
But will the function return both of them, sir? And we pick out one, is it?
Yeah, we will pick out one. Function will return one, and we will pick out function will give you the very first one.
Okay.
So we have training data, we have model, we have loss function. Now come to the optimization process. So here for the illustration, we have used MNIST data set. In MNIST data set, we have classes from 0 to n. So and inputs is the form 28 by 28. So you already have seen this in the week 5.
So in MLP, we use MNIST data set from another source, and here we are using it from Keras. Why is that so?
No, you can use from any of those.
Okay, both are the same.
Both are the same. Yeah. So these are your actual classes. I'm actually coming to the optimization procedure. So remember, we have to do one-hot encoding because we are actually finding out the k linear combinations, k different different linear combinations for one example, and so that we have to use one-hot encoding to transform our label vector to the encoded vector. So what does label one-hot encoding means?
We put ones for whichever class it belongs to.
Yeah, exactly.
So could you explain this particular code that why one hot NP array a range?
Okay. So I will explain this code. So first, give me one. Let's take one example. You have three classes, classes 1, 2, and 3. Okay, it can be 0, 1, and 2 as well. So just make small changes in there. Okay, so you have three classes, and let's say you have n examples. Okay, so your pi will look for one first example by your label vector will look like something like that of the shape n cross 1, right? Now
Yes, sir.
assume that you have four examples. So your label vector will look like something like of the shape 4 cross 1. And let's say first example belongs to class 2, second belongs to class 1, third belongs to class 3, and the fourth belongs to class 2. So this is your label vector. Now if you have encoded that, you need to encode that. So what will be the shape of encoded matrix?
4 cross 4.
4. Yeah, 4 cross
4 cross 3.
4 cross 3.
3.
Each row corresponding to each examples, and each column corresponds to class. Okay, this corresponds to class, and rows correspond to examples. So first example belongs to class. So you have class 1, class 2, class 3. So in the notation you will use class 0, class 1, class 1, class 2. That you can do. Always you can transform into this 0, 1, 2 thing. If you have classes like 8, 3, 5, let's say you have only three classes. So you can transfer back into, it's just kind of encoding, right? So 3 you can encode at 0, this you can encode as 1, you can encode this as 3. Okay, so only matters is how many classes are there. Okay, so for if this belongs to class 2, then the corresponding column. So this is 0th column, this is first column, this is second column. So corresponding column belongs to becomes 1, and all others belongs to 0. Right? Okay, so this is 0, this is 1, this is 2. So this will become 0, 1, 0, and for 1 it will become 1, 0, 0. For 3 it will become 0, 0, 1, and for 2 it will become 0, 1, 0. So this is your encoded matrix, right?
Yes, sir.
So now look at what's happening in the code. So actually, first we have taken zero matrix of the shape length of pi. So let me share the entire screen first. Okay, so here what's happening? So first we are taking every zero matrix. So what will be the shape of zero matrix?
It will be 4 by 3, sir.
4 by 3. So it is number of examples.
Yeah,
the number of examples into number of classes, right?
Yes, sir.
So here, so look at here. So zero matrix is the number of examples and the number of classes.
Yeah, yes, sir.
Now look at the entries. So remember, for the first example, so this index is what? This index is what? The first example and the class, right? So this actually is the number of examples. This 1, 1, right? Index. The first index is 1, 1. So first example, first class, right? So this index belongs to first example, second class, right? So we want this entry 1 where the class is 2, right? If it is class 2, then it makes 1. Here it is class 1, then the corresponding first column becomes 1. If it is class 3, the corresponding third column class becomes 1. And if it is class 2, then the corresponding column becomes 1. So now look at here. Look at this code. So the entry. Here it is np arrange.name will give the example, and the second index will give the class, right? So if y is 2, we will set it to 1, and all other are already zeros.
Okay, so sir, the len of y is not actually the entire length at one go. It is whichever row we are in, basically.
The length of y actually will give you the number of examples.
But sir, here in our case, it is 4, right? So it starts off from the 4th one. Doesn't it mean that A range?
NP arrange means it is a sequence from 1, 0, 1, 2, 3.
Okay, so up to
NP
3.
dot arrange. Yeah. So it is actually NP dot arrange 4. NP dot arrange 4 means you have a sequence 0, 1, 2, and 3.
3. Okay. And then y is whichever class it belongs to.
Which is class it belongs to. So it is actually this entry. If let's say for by hot. So here we have to start loop, right? We have to start loop, right? In this particular code.
I beg your pardon, sir. Could you repeat that, please?
We have to start the loop.
Yeah, we have to start the loop. Yes, sir.
Yeah, this is the, I think, wrong code here. We have to start the loop here because
that's what I was getting confused, sir.
Yeah,
because
so it will give only one column, right?
Yeah, it will give only one column there.
No, actually, no, it's right. It's right. Because remember here it is np dot arrange by. This is the array and by is again a array. And the end dimensional array. So it will take care of all such columns, such indexes.
So when you have np dot arrange, so then you will have 1, 2, 3, and it will go one by one in loops. Is it, sir?
Okay, so let me explain this.
I get confused with its arrange and reshape, sir. Both of these functions actually.
Now remember the array 0 vertex. So you have 0 vertex, 0, 0, 0. This one is 0, right? Now if you want this this index, and this index to be 1, right? So what
Yes,
np dot arrange for do? It is a 1, 0, 1, 2, 3, and what is by? By is 2, 1, 3, 2, right? So this will become, so again I'm transforming into the 0, 1, and 2. So this will become 1, 0, 2, and 1, right? So here it will take 0, 1. So 0, 1 index. So 0, what is 0, 1 index? This one. 0th row, first column. So now this will become 1. This will become 1. Now second, what is second? This is 1, 0. 1, 0 means that first row and 0th column. So now here it will become 1.
Okay, got it, sir. Yeah. This is better.
So this is what happening here. Okay, so this is how you will convert a vector into an included vector. Model we have already seen. We take the linear combinations, we pass through the software function, and then make the predictions of how. So this we can write it as x cross w. So w here it is of the size m cross k, right? Because for m vectors for each class and k classes are there, right? And we pass this function into the softmax function. So what is softmax function? We have defined or not? Not yet. Okay. So the probabilities actually we are passing this. We are actually calling those values as the probabilities, right? So there is some error in this code. I don't know what. Okay, so here it is softmax defined. Softmax is defined as exponential z. So z is what? Is the linear part. Z is the linear part, and we take np dot x. So here for the just for numerical stability, we have subtract maximum of those, and you can avoid this part as well. Okay, so this is just for it doesn't go up to very high value just because of that. Okay, so you can avoid this part because remember denominator is the same for all such k values, right? Denominator is same, only changing is the numerator. So if it's just kind of shifting to left, right? Each value is shifting to the left, so it won't change the order. So you can avoid this part as well. Doesn't make much change in the model. Actually it doesn't make any change in the model. Okay,
so we are trying to normalize here, is it, sir?
Not normalizing, we are just stable. These values doesn't go very high, doesn't take any high value, to make sure that we are just separating to the maximum value. Okay, because if let's say z is coming out to very high value, so it is e raised to power something, so again it will exponentially rise, right? You can avoid this as well. Doesn't make any change in the model. Okay, so every time we are dividing the values with the sum, right? Denominator is the sum of all such exponentials, and in the numerator for each and every k classes we have numerator as e raised to power that sum, right? And returning that array. Okay, so this will return your an array where it will give the probabilities, corresponding probabilities, right? Okay, so next come to the loss function. Loss function is defined as by k log by k head. So it's again cross entropy loss function that we have discussed over k classes, right? And this is just for single example. You can sum it over all such n examples. Now next part is the optimization. So for optimization we will use standard gradient descent. For finding standard gradient descent, we have to find the derivative of this loss function with respect to the weights, right? Weights means that w's and the vi's. So remember these notations. So this is the coefficient of corresponding to jth example and jth features and that ith class, right? And bi is the bias for the ith class. So all such derivative we need to find. So how you will find those derivatives? It's just all mathematical part here. Okay, so for that finding the derivative, let me it's all mathematical. Let me do that because it may confuse you as well if you go through the lecture. Okay. So for that, you know two rules for derivative and derivative. Let's say y is a function of g of x. Let's say y is a function of g of z, and z is again a function of x. Some other function. Now you have to find the derivative of y with respect to x. So how you will find the derivative? Y is a function of z, but z is again a function of x. So ultimately y is a function of x as well, right? So how you will find the derivative of y with respect to x? It's just finding the derivative of y with respect to z, because now y is a function of z, and then finding the derivative of z with respect to x, right? This is one rule, and another one is that let's say y is a function of some function of x and y. Okay, and x is a function of z. Let's say h of z, and y is again a function of z. Let's say some other function g of z. Now you have to find the derivative of y with respect to z. But if you notice, y is a function of x and y, but ultimately x and y are the function of z, so ultimately y will become a function of z as well, right? So how you will find the derivative of y with respect to z? Can anyone please give me the expression how you will find the derivative of y with respect to z?
Sir,
Yes.
I think first we find the derivative of partial derivative y with respect to x and y.
Okay.
Then here we will multiply the derivative of x with respect to z and derivative of, yes, like this, yes.
You already have seen this in the maths course, right? This is called chain rule. So these rules we will apply to find the derivatives. Okay. Now come to the loss function. So remember here loss is the function of y, right? And y is the function of z, right? So remember z is a function of yk log yk n, right? K belongs to 1 to k class is there, so okay, just use this notation. Now this yk is what? Yk is e raised to power z I. Okay, so let's call this j, because this will make confusion. This is, let's say, called j. This is j, and so j for j we will make by ej upon sum over e raised to power z I. I will 1 to k, 1 to k, right? K classes total. So remember, j is a function of by k by j, and by j is a function of zi, and zi is what? Zi is what? Linear combination. So this is bi plus, so call it I. Really better. Call it I. Okay, so bi plus the w J sum over W J I.
So what is I? This will be log.
So J here it is feature. So X corresponding to X Jth feature, we have W J, and I is denoting to class.
So
I
in the
is denoting
top
to class.
equation, that J will be I.
Hmm?
This will be log y hat I.
Yeah, this will be pi hat I.
Okay, and this e to the power of I, and this will be 1 to j, the divided by sigma 1 to j. J is equal to 1 to k. Right,
Yeah.
right.
So
So could you rub it, and because
okay.
I'll make notes afterwards, I'll get it.
Okay. So these notations are very quite confusing, right? So once you know what are J, what are I, what are first index, then it will be all clear. Okay, don't be
Right.
confused with it. I'm using the same notation because the sir is used in the lectures. Otherwise, I can use the same one that we already use in all other lectures. Okay, so
Generally, the first is the feature and the second is the class, right? Wherever it is coming.
yeah, first is the feature, second is the class. Okay, so loss is defined as by I log by I hat sum over k classes.
And it'll
Right?
be negative, right, sir?
Yes, sir. Yeah, negative. Always take care of negative sign as well. Okay, now what is pi I? What is pi I hat? It is e raised to power zi, right? Upon summation over e raised to power zi zj. J is summing over 1 to k. Right?
Sir.
And what is zi? It is the linear combinations for the ith class. So it is bi plus w. Here it is j in ith class, and it will become the jth feature. Right? And summing over all such features. So here j will vary from
So shouldn't the W be IJ?
wd.
I mean, the W in the bracket, what you've written, shouldn't it be IJ for the ith example,
No.
the jth
Here
class?
here for ith class and jth feature.
Okay.
So it will vary from j is equal to 1 to
K.
m
N. Sorry. Yeah.
feature. Right? So remember those things. We have seen that
Right.
how to find the derivative. I will make use of this chain rule. So actually, I'm to find the derivative of j with respect to wi's, right? But here, look, if you look at here, this is the function of by I hat, right? And by I hat is the function of zi's, and zi are the function of wi. So ultimately, the loss is the function of weight vectors, right? So what you have to find? So you have to find del j upon del.
Wait. Right.
One thing is pi. And another thing is weight vectors. So all those weight vectors. So it is w, j, and I. For all such j is varying from j is for feature and I is for class. Okay. So these two things I need to find. Okay, so I told you j is a function of by I hat. So what I will do, I will use the chain rule. So I will find derivative of j with respect to by I hat. Can I use the slide directly because it will be time consuming? Okay, so can you see the pull-up file? Okay, so what here I have to do? So for finding dj by dw for ji, I will actually find out first dj by del z and del z by del w, right? This expression is okay.
Yes, sir. It's okay.
Okay, so first I need to find these two values, right? So first find out del z by del w. So this last one I will find here. So remember what is ji? This is the linear combinations, right? So and we are differentiating with respect to wji, right? So what will be the differentiation of this thing, this particular thing? If you look at here, this is your zi. If you take derivative of this thing with respect to zi, right? So all other coefficient will go 0 because we are particular one weight we are differentiating, right? So this is actually bi plus w1i x1, something like that. So all these coefficients will go 0 because this is constant. We are differentiating with respect to wji, right? So only the coefficient, this coefficient will remain. Okay.
Right, sir.
So this derivative will become x. Now what we need to next, we need to find this derivative as well. So this derivative, and again for the intercept, again we have done explicitly. We can see it as a we can find it out as well. So next we have to find this derivative. Remember zi. So zi is again a function of bi i's.
So which one is this one? The first part, is it? I mean,
For finding this thing. So this we
Okay.
already find. This
Yeah.
we already find. Now we need to find this one, right?
okay.
How's that one, sir? This equation 4?
How this is?
Coming to 1.
Because this always go to 0. We are differentiating with respect to pi.
Right.
All these coefficient will become constant. All these will become
Right. 0. Right.
constant. So only this is your variable now.
Right. Right.
So
Right.
this will become 1.
Okay. Right. Right.
Okay. So remember j was the function of bi hat, right? So first we have to find the derivative of bi hat, and then we will find the derivative of bi hat with respect to zi, right?
Right.
And again remember one thing as well, because bi I hat, this bi I hat is a function of, I mean that zi. This may confuse
This
you.
step is confusing, sir.
So you have to find dj upon del zi, right? That you have to find, right? So what is j here? J here is a function of bi I hat, right? And summing over all such classes. So this is the function of bi1. This is the function of bi1, bi2 to bij, and j hat. Right? This is a function of bi1 and bi2 to bij hat, right? And all these are the function of zi's, right? These are the function of z, because remember in the denominator all this comes, right? For bi1 hat also z e raised to power z1 comes, z2 comes. So all these zi's come into the everyone's, right? Is that
Yeah,
clear?
yes,
J
sir.
is the function
Yes.
of this thing, and all these are the function of all those linear combinations,
Yes, sir.
right? So now look this derivative. So for this derivative, first I will find the derivative of j with respect to particular that by k. For if we are finding derivative with respect to ith class, so we will find for by I hat, and derivative of by I hat with respect to what?
Z.
What will be this? Zi.
Zi.
Z.
Right? Plus remember j is the function of all j is the function of zi, all zi's. So we have to take care of as well. So we have to take del j upon all by let's say k now, okay, or say other index. So these index are very confusing now. So let's say this is j. So j is coming for feature as well, and this j is again here. J is not equal to I because I have already find out explicitly for I, right? So j is not I here.
So this
derivative-
plus sigma is not clear. How did you get this?
No, I will find this explicitly. This thing I haven't found, right?
No, this portion is clear.
Yes.
Then you are adding this. What is this portion?
This heading, right? Because J is
Yeah.
a function of all such by i's. It's not a just function of by I head. It's a function of all such by i's.
Right.
Right? And all
Right,
by I is a function of Zi.
So to make myself clear, is that because the Zi, when we calculate, we have that denominator as summation of all? Is that the reason why do we do the sum?
That's why I'm calling each and every by I is a function of Zi.
Okay.
Okay. Or if you are getting confused, just think of this thing. Just think of this particular case. Let's say y is a function of x and y. Not, let's say, let's call it some other variable. Let's say p and q. Okay, these are two variables, and p is the function of x and y. P is a function of x and z, and q is again a function of let's say d, x and z. Now you have to find the derivative of y with respect to what? Something is confusing you, right?
Let's say with respect to z, sir, can we find dy by dz?
Okay, then we will find del z by del p, right? And p is again function of z, p z. But again, remember g is again a function of q, and q is again a function of z. So for that, you have to find g of del z, del q, and q with respect to z, right? So same thing we are doing here. J is a function of all because we are finding derivative with respect to ji, and j is a function of what? J is some function of that
Yes.
by case.
So even for x, it will be the same, sir.
By k
If you
head,
do
right?
del
And
y
all
by
these
del x.
these functions, all these are the function of zi's. If you are trying to connect this thing, y is a function of p and q. So j is a function of by one head by up to by k head, and all these. So p and q are a function of z. So all these are a function of zi's, right?
Right.
Right. So what you will do, you will find the derivative of this respect to all these. So you will find the derivative of dz with respect to all these variables, right? So you will find for by j all such variables. So now come to that part. So you will find the derivative of j with respect to all such variables. Okay, here I'm taking explicitly by here because this derivative will be different, and all other. So where j is not equal to I, all other is taken care
Right.
of.
Clear, sir.
Right?
Clear, sir. Thank you.
Clear. So now you need to find this derivative, and this derivative. Okay, so if you will do by yourself, all things will be clear. Otherwise, you will get confused. So do it by yourself and use that chain rule and all. Okay, so now you will find this thing. So now this is the just function of by head. So what will this derivative? I'm finding with respect to this particular variable by I, and this is the summing over all such variables by one head, by two head, up to by k head. Okay, so all other terms will go zero. Only the term which contains log by I will remain, right?
Clear, sir. Right, sir.
Okay, so what is the derivative of that? It's just a log derivative. So it is 1 upon that variable. Okay, so this will become by I upon by I head. So So this is the actual one. This is the predicted one. So, right?
Right.
Next, so we have found
But
this.
why didn't we differentiate yk again? I mean, generally when we
No. So look at this term. We are finding derivative with respect to this variable by I,
yeah.
right? And here, look at the terms here. So it is by one
Y
hat,
hat.
by two hat, and all those variables will be zero because we are derivating with respect to this variable by
Yeah.
I,
Yeah.
right? So this should be hat here. This should be by I hat. This one by I hat.
Yeah. So then we get divided by y hat I, and
Yeah.
okay, yeah, this is y hat, right, sir? Okay, then it is okay, sir. Yeah, got it.
Okay. So this derivative we have found. Now this derivative. Okay, so this is we are finding with respect to I, now with respect to j as well, because here in this particular terminology all such derivatives are coming, right? So for particularly I we have found, let's say, okay, so first let's found this one as well. So this one is by I hat upon zi. So what is by I hat? This is e raised to power zi upon summation over e raised to power zk over such k, right? So this is the expression of by I hat. Now what will be this derivative? So look at the variable here. So this is variable here. So all these all variables are coming in the numerator as well and in the denominator as well. So we will use p by q form of derivative, right? Quotient form. So first variable derivative of first variable and the lower denominator one is the same. In the minus, first one same, derivative of the lower one, right? And the square of the denominator. So you know this formula, right? P by Q, derivative of P by Q form.
Yes. Sir.
Yes.
Okay, so if you find this derivative now, so what is this derivative? It is a derivative of e raised to power x, because the variable is zi and here it is e raised to power zi. So it is just e zi, right? E zi. Okay, so and this derivative, this is sum over all e raised to power zi, but we are differentiating with respect to zi. So all other will go zero, only e raised to power zi will remain, right? E raised to power zi will remain and all other will go to zero. So this is manipulation now. So for this particular term, one square term will be cancelled out. So you will remain e zi upon this summation thing, right? So remember this term, this particular term. So this will become by I hat, and here, yeah, this will become e raised to power zi square, and this is already a square. So this is what? This is again by I hat. So this will become by I hat minus by I hat square, right?
Right, sir. Clear, sir.
Clear. Now we have found this one as well. We have found this one as well. Now we have to find this two as well, right? So this for finding this two, first let's find this one by I hat upon zi. By I hat upon zi. So here, what was the difference? Here in the denominator, it is the function of zi, but here it is the function of, it is a constant now because we are differentiating with respect to variable zi, right? So that was the difference. Here it is the denominator was the function of that variable zi, remember. And here we are differentiating with respect to zi, but in the denominator we have constant. So we can use that formula 1 upon x. What is the derivative of 1 upon x? Leave out these two terms. What is the derivative of 1 upon x? Minus 1 upon x square. So minus 1 upon x square. So x is what? This. And we have to find the derivative of this thing as well. So this thing, right? So what will be the derivative of this thing? This was the constant. So constant I put as it is. Minus coming out, the derivative of 1 by x is minus 1 by x square. And what is the derivative of this with respect to zi? This thing. The sum over all e raised to power z1 plus e raised to power z2. So all this term will go zero. Only term e raised to power zi will remain, right? So e raised to power zi term will remain and all other will go to zero. So you can use the quotient rule as well, and you can also do directly 1 by x is equal to minus 1 by x square. Okay, so if you manipulate this terminologies, so
could you repeat that again? I mean, I didn't understand. Del by del zi you do. The top one is a constant.
Top one is a constant. Here it is a function of the variable. Variable is zi, right? So this is the derivative of 1 upon function of x.
Yeah.
Right. So what will be that derivative?
1 upon x square minus 1 upon x
so
square.
This is something like del up. This will be something like del upon 1 upon f of x, or let's say some constant term f of x with respect to function x. So what will be this derivative? This is c upon f of x square of x square upon f dash x, right?
Okay. Yeah.
Derivative
Yes,
of
sir.
1 upon x is minus, sorry, minus will come.
Minus 1 upon x
Minus 1
square.
upon x square, right?
Yeah.
So this is what happening here. So this was the constant and this is the function. So 1 upon x square. So 1 upon function square, right? This function square. Now you will take the derivative of this function as well. So all other terms will go 0. Only the term containing zi will remain, right? So it is to zi will remain.
Yeah.
So
Got it, sir.
Yes, sir, yes.
separating out these two terminologies. So this will become by j hat and this will become by I hat. Okay, so remember here it was coming out by I hat minus by I hat square. Here it is coming out as minus of by j hat by I hat. So now we have found this one as well, right? Now this one, all things you have to do. So this thing, can you do this part? Okay, so all these things you have found and you have to put all these things back into the equations. Okay, now it's just the manipulation part, just putting all those derivatives into the one by one in the kind of back propagation back you are finding, right? So you can find out this derivative. So this j del j by del w will be xj minus by I hat minus by I hat. So this remember we have taken loss on corresponding to only one example, right? We have taken loss corresponding to one example. So for all n examples, you can write it as in the matrix form. So this will be the derivative of loss with respect to w x transpose by hat minus by, and with respect to the intercept part is easy. So you just go through this derivation, this derivative part. Okay, try to understand that and do by yourself. So that will be easy. Okay, so this is your derivatives. And what is the weight update rule? Weight update rule is just the gradient descent. So in the t plus 1 iteration, we just update by alpha and derivative of this. So this part you all know, I think. So that's how you train a
Sir,
softmax
generally
regression.
in all other models, we don't use this bias term separately, but here we are using it.
Yeah. So
why
yeah.
is that so, sir?
No. There's no such actually. Just because of these derivatives kind of things, we are separating it out. Otherwise, all things are okay.
Because that loss function, the gradient descent formula is the same for everything, but here we have additional bias term, which we generally don't look at.
You can include into weight vectors as well.
Okay.
It won't affect your last value. It won't affect your derivatives. Okay.
Yeah.
So one doubt is there. You're using MLE for getting the loss function, right? Now, why aren't we differentiating and equating to 0 for the maximizing? Why are we using gradient descent?
Here we are using log likelihood, and that is called cross-centric function. So your question is why we are not using normal equation, right?
Yeah.
Yeah, that we can also do. That will give some different solution. But here generally we use in all other part, even in the linear regression or other models, we generally prefer gradient descent rather than normal equation.
Okay. Right.
Okay. Okay, so for coding part, it's just writing these equations. Okay, so Z is the linear combinations, and we are finding the by hat as the output of those variables, right? Z is linear combination. We have defined softmax function earlier, and we are encoding those. So by hat, we are by was your actual class, actual label. Okay, so we are encoding that using that function that we already defined. Now we are finding gradient. So gradient was x trans. So gradient was the this gradient, right? So gradient was actually the dot product of X transpose and by hat minus Y. So you were saying that by B is not part of W. Even if you take the B as a part of W, the same thing will happen, because X transpose here, that X, you will add dummy features as well. So the same kind of thing, you will not get any difference here. I don't know why the different notations and why different things are used here, but same thing is here. There's nothing different. Okay, you can include V as in the W vector as well. Okay,
So
so
in that, so if we include that, then we don't have a separate B term, right, sir?
Yeah, separate B term we don't have. We have to add dummy feature into X.
Yeah, yes, sir.
Okay, so this is how you are finding the gradient by taking the dot product of X transpose and by hat minus Y, and B hat is just the by hat minus Y, right? And 1 by n just 1 by n is just for mathematical just convenience. You can drop it out as well. It won't affect your value because it's just a constant. It will be cancelled. It will cancel it out by the linear rate or something like that. So it's just for mathematical conveniences. No other reason for that. Okay, so how you update your weight vectors? It's just linear rate into gradient, right? So gradient you can find out in this using these expressions.
So is it because we are doing one hot that we are not taking dummy feature, and we are taking B separately?
No, there's no relation in that adding dummy features, and we are encoding only the labels, not the features.
Right. Sorry, yeah, wrong question. Right.
Okay. So loss will be got. Now it will be some. Okay, so here it is taken mean. Okay, so it is minus of log, right? Minus of logs that by hat, and this is the encoded matrix here. So by, I don't know why it is mean taken. I think some should be there. Okay, and for every epoch we are finding out, for every epoch which are for, I think the 10th epoch we are taking we are finding out the loss. We are taking print of the loss for every 10th iteration, 10th epoch. Okay, and this function will return your weight vector, intercept vector, and the losses.
So could you confirm either through discourse or maybe in the next session whether it has to be a mean or a sum? Because then
this terminology I'm confused by. This should be mean.
Yeah,
this
because
should be some,
otherwise
when
we code, then it may create a
I will
problem.
confirm with the team. It should be mean or the mean should or sum.
Yeah, yes, sir.
Okay. Okay, so how you will make predictions? Similar kind of thing. You take the linear combination, you apply the softmax function here, and then take the maximum argmax, the maximum value, maximum index, right, for that probabilities. So this function is pretty easy. Accuracy, you checks which one are predicted correctly. So these are predicted correctly, and overall such by. So this will give you the accuracy. Okay, and now we have applied this all class, or we didn't define the class, we defined that separately functions. So we have used all those functions for training our MNIST data set. Okay, so fit, remember fit here, fit is function is returning 3 values. One thing is weight vector, intercept vector, and the loss function. So we are calling as W, V, and L. So this function will return these weight vectors, intercept, and the loss. And for every 10th epoch, right? So 0th epoch, 10th epoch, 20th epoch, up to 90th epoch. Because total are 100 epochs here. Okay, so this is the corresponding loss there. Learning curve. L here. So L here we are calling as the loss, right? After the 10th epoch. So we are finding the we are plotting the loss function here. So this is how your loss function is looking. So you can check it out as well. There's 4.62, then 1, then 0, 0, 0, decreasing down, right? So it is decreasing down sharply here, exponentially decreasing, then going exponentially down. So sharp decrement and then slowly decrement here. So you can predict the values using the function predict over the training examples using that weight vector. So weight vectors we have fit using the function called fit. So W and P we are taking out from this function. output of that function, and we are using that weight and bias for predict our training data set, prediction for that training data set. Okay, and then accuracy we can find out. So accuracy, again, we have, I think, defined, yeah, we have defined accuracy as well. Okay, so all these functions we have used for MNIST data set. Accuracy is coming out to be 0.8. It is very good. You can also make the confusion matrix for that. For confusion matrix, you can make use of sklearn library. Okay, so all these things I think you must have seen before as well. Yeah, so this is all about the software regression. I think we have wasted up 2 hours only in software regression. We have 2 things pending as well. One is general linear models, and second thing is KNN. So should we continue on this part, or should we have a different session for GLM and KNN? We are remaining with 2 things. One, general linear models, and second is KNN. So I think we should have in the different session because it will take more than 1 hour as well.
Yes, sir. Okay. And
Sorry?
yes, can we have a separate session for the other two?
Yeah, I think we should have separate session. Otherwise, it will go long.
So, and you will take it, sir?
Yeah, I will take it.
Right, sir. Because thank you. This was very helpful. At least the math
Okay, so
got
it will
very
be more
clear.
helpful if you go through the lectures and try to understand what's happening. Because softmax now it should be clear. So go read it out and try to do yourself. Try to do that derivative by yourself. It's all mathematical. Just don't be into notations. Models will be clear how you're defining loss function and how you are optimizing these things. Okay. All other things are the mathematical.
Right,
Okay.
sir.
The next thing is GLM. That is again important part of this week 7 that needs to be done. And KNN it is. It should not take much time for KNN, but GLM should take more than half an hour. So I think we should have session on Wednesday or Thursday. Which one will suit you?
Any day, sir.
Okay, so the same timing is okay, 6 to 8 or any other time. So how I should convey this thing? So when we should take session or not? This course will work.
Yes, sir.
So I will give the timing and the day for the next session. So I don't know how to convey to all others. Okay, I will figure it out.
I'll put it on WhatsApp if you want, sir. I can put it on WhatsApp. Whoever is there, but it may not go to everyone.
WhatsApp group for MLT. You have separate groups.
Yes, sir, we have for MLT, but it may not go to everyone. But I think it'll be better if the institute informs everyone.
Okay. I will try to find out. I will figure out how to convey to all the students. By the way, in the next session we will have the generalized linear model, not the general one. Generalized linear models and KNN. So it will be better if you read it out.
Right, sir.
You go through the slides. At least once you go through the slides, try to understand what's happening there. So it will be easy for me as well.
Right, sir. But thank you very much for today's session, sir. A lot of concepts got clear.
Okay.
Sir, we don't have any classes on Thursday, so you can. I think that would be better.
Okay. I will try to have it on the Thursday because we have solved the session on the Saturday as well, right?
Yes, sir.
So we'll try to have it on Thursday. Okay, Thursday will be okay for me as well.
Sir, I would suggest that you have it regularly on Thursday because MLT requires 3 sessions is what I feel.
Okay, 3 sessions per week, huh?
Yeah, because generally every week I see that we are not able to complete all of it. Almost all weeks we have this problem of having to leave certain things out.
Okay. I will convey to the team so we can have 3 sessions per week.
Yeah.
Okay.
Yes, sir. I'm also agree.
This is all about for today's session. Then we will meet on Thursday. Okay, so any questions?
Sir, time, what will be time, sir?
No, I'm not sure though. Mostly 6 to 8 or before that. Anytime will work for me.
Okay, sir.
I will tell you.
Sir, some request is there for this course MLT.
MLT.
No, MLT, this particular
Okay.
machine learning technique. So whenever we try to read and that, so what's happening, sometimes the video is hard to understand, like that generalized linear model is there. The first video,
Hmm.
it took the so much time that what is the motto, that how it's I comprehend, because sometimes we see that this subject
Hmm.
machine learning technique involve everything, so comprehend everything all together takes time. So is it possible to make the some hierarchical chart like that, because the machine learning involving the many area and the many possibilities there. So if we go on the net to learn that, so many branch go from there and very limited syllabus for us. So easily we get divert from that topic. So is it possible to make the some hierarchical theoretical type of thing somewhere apart from that syllabus, so we can see that what we are studying and what is the use of that, and the some basic example, for example, we was talking exponential and why it is exponential, we knew okay it is through the mathematical way and through this particular theory, but actually I want to visualize that. So how will I visualize if there will be some basic data, basic example, and somewhere the data will be there based on that. So I can plot, I can visualize, I can practice this instead of finding our data my way. So that all the things I was thinking to tell you
Yeah,
from one of
I
my.
got your point. Actually, in this term, it's very hard to put all these things because we are working on the improvement of MLT side. We will certainly will try to give you the notes for MLT, and in this, I'm not sure whether I cannot commit that we will provide you or not, but we'll try to provide you some notes on MLT side if it is possible. Okay, so that may help you because it will cover all the things that we have covered in the lecture and the more things as well that should be there. Okay, there's some missing part in the lecture that we will try to cover in the notes part. So possibly
Correct.
if we can do that, we will definitely try. Otherwise, I won't commit for now. Okay.
Okay, okay, sir. Even that the basic thing will be clear that why we are doing and
Yeah,
what is
that
the.
part I got your part. Some part is missing in the lecture that we are trying, actually we will certainly try to provide you.
Yeah, sometimes the mathematical gap and that this programmatically and the philosophical, these three all thing is combined in this topic. So suddenly its jump is there from here to there.
Yeah, we understand that. We will definitely make some changes in that.
Sir, even this
Okay.
derivative which you did today, I mean, had we gone through it on our own, I don't think at least I would have understood that derivation. It is only because you went step by step that I understood. So that kind of thing is not happening with those lecture videos.
Yeah, I understand. I completely understand that, and this problem we are facing from the last term as well, and certainly we are trying to improve those courses. Okay, so that's why we are having these sessions. So if you go to the live session, you will find that we are trying to fill those gaps. Okay, so let's see what happens. We will certainly try on that. And the derivative part, actually, this is nothing but mess up thing kind of because lots of notations are used there. So that may confuse. Otherwise, it's very simple derivative. Nothing very hard formula, nothing very complex functions is used. It's just a linear combinations of variables. Like, but just because we got confused which variable we are differentiating along and which expression we are differentiating, that's it. If we come to know that derivative is pretty easy.
Yeah, yes, sir. I mean, when you went through, it was quite understandable, but all the J's and the I's, it becomes too much to understand.
So
actually.
Just make sure that along which variable you are differentiating and which expression you are differentiating, right?
Yeah.
Do that derivation by yourself. You will find it very easy. just go through that slides once and then do by yourself. Okay.
And one more thing, sir. That sometimes sir say that we are try to solve that everything from the scratch, and that in this lecture they use that keras, and when I went to the keras, then it said
Keras.
that that
Where
module is
keras is used?
whenever he was showing that in that one.
In loading the data, I think.
Okay. Only for loading data set keras is used. Otherwise, we have used NumPy, Pandas, and for MLT side we have used sklearn. That's these three libraries we have used. I mean,
Okay,
for the plotting and matplotlib of Cvon. Otherwise, keras is not used for the only for loading the data set, MNIST data set. We have used the keras.
Okay.
Keras library is mostly used in the deep learning for neural networking.
Okay. And one more thing. So suppose that we will able to develop this idea. Suppose someone has gave the data and nothing else, only the data we have, and there is a lots of algorithm. Is that what is the basic steps to design that?
So are you on the MLP side as well, or only MLT you have chosen?
MLT.
Only MLT.
Yes.
So you will go to MLP side. You will have certainly such kind of questions because you will be given a data set. Now you have to do different modeling over there. Once you know it's regression classification, because now you have lots of techniques available for regression and for classification. So which one to use? So this kind of answers you will get in the MLP side, and definitely you will have project this semester, this term and next term as well. So this you will get answered there.
Okay, I thought I purposely choose that MLT only, not an MLP, because I wanted to understand this thing, because sometimes I have seen that the way MLT solve and the way we use the model there in the MLP. So before using the MLP in that way, I thought to get understand this mathematical and solve our way.
Yeah, that is the right way. That is the correct way. That's why the MLT is the prerequisite for MLP. Prerequisite, I mean.
Okay.
That is the correct way. That's the only way for learning machine learning. It's not just writing 2 lines of code. You should know what's going behind the algorithm. Otherwise, you cannot set your parameters there. If you go into MLP side, you will have you have just one estimator. You will apply to the estimator. Pre-processing is a different part. You will see that. But once you have pre-processed your data, you will write only 2 lines of code for the estimators, right? So in the estimator, you have to set different parameters. So for setting those parameters, you should know what's actually happening. What are those parameters, right? So what those parameters, actually, if you know the algorithm, you know the MLT side, then only you can understand those parameters. Otherwise, it will be just writing, copy pasting the codes. That's it.
Okay. So we can develop this thing after understanding, after doing the
Absolutely. If you don't know what's going on behind the algorithm, it doesn't make any sense to writing the codes. Right? Okay. You can certainly do. You can just write codes. You just copy paste from anywhere. It's just 2 line of codes. The estimator, and if you are using some hyperparameter tuning, some different 3 or 4 lines of code. That's it. You are done. You are done with the models. Pre-processing part is another part of this modeling. But once pre-processed, you need to write only 2 lines of code. So for those writing those lines, you should know what's going on behind the scene.
Okay. Okay.
Okay, so I think we should close the session now. We can have one more sessions before the solve with instructor. So so I request you all to go through the slides at least once, because there's not much cover in week 7. Only 3 major topics: softmax regression, KNN, and the generalized linear models. Okay, so KNN you will obviously find very easy, and you may confuse in GLN, but it is again a very easy. It's a generalized form of linear regression. All other models that we have done, linear regression, logistic regressions, whatever we have done, it's a generalized form of that. Okay, so we will see that in the next part. So I think we should close it now. Thank you everyone. Thank you for attending.